All right, so I don't know. I don't remember how far we got last week. So let's talk about inferential statistics real quick. Inferential statistics is usually used with, or not usually, it's we see it the most with like studies that deal with trying to determine whether a particular treatment is producing some desired outcome. Okay. And one of the easiest places to see it is in like pharmaceuticals. Okay, if we're making a drug that is supposed to maybe, let's say, cure cancer or a particular type of cancer, we would be interested in how effective that is, right? Okay, we don't want to just give it to people and say, well, we think it's going to work, see what happens. We want to know, based on this ailment, we have this treatment, and we can determine with some level of confidence its effectiveness. So what they do is they will hold studies, okay, and they will, some people, you guys ever heard of like, they're experimental studies, experimental treatments, okay? So you can, as a patient, elect to be part of those. Now, when I'm a patient, they have things called single-blind studies and double-blind studies. And double-blind studies are like the world, like that's the standard. That's the what with the benchmark. Does that kind of make sense? Like talk about what they are. And we'll talk about them. They'll actually be defined in notes at some point. But a single-blind study. Let's say that you guys are in my study. Okay, so I want to know the effectiveness of this drug on some population of, let's say, cancer patients. And let's say, obviously, I can't go and give this drug to every single cancer patient, right? So what we do is we take a sample, okay, and that sample becomes part of our study. And what we do is we say, okay, we're going to break that sample up into some groups. We'll have a control group. Let's say this side of the room is our control group, which basically we're not going to do anything with you, okay? We're going to give you a placebo, which is like a, if it's a pill, it's like a water pill or a sugar pill. If it's a shot or something like that, it's probably like a saline solution or something like that. Something that you don't know that you're not getting a drug, but you don't know that you're getting a placebo. Does that make sense? Okay. You guys are going to be our treatment group. You're going to get the actual drug. Okay. And what we learned from that study of these, let's say, 20 people, will then give us an idea of what we can expect inside the population, okay? Now, if we just do one study, let's say I want to talk about the population of all people that get, let's say, I don't know, like lung cancer or something like that. If this is a drug to treat that, there's no way, research-wise, resource-wise, money-wise, that we can go and deal with every single person, right? So if I do just a study of just 20 people, that's probably not going to be enough to say, yeah, this thing works, right? Okay. We do multiple studies. We do 3, 4, 5 studies, okay, with different groups of people to see, okay, now I've got this, we call it meta-analysis. We've got data from multiple studies that we can look at and determine if this drug is useful or not. Does that make sense? Okay. And a lot of times you find out that a drug that was designed for one ailment doesn't fix that ailment, but because of monitoring those people, we find out, oh, this drug was maybe it was designed to treat a certain cancer, but now we see that it's reducing blood pressure. So maybe now it gives an idea for the pharmacist or the pharmaceutical company to kind of maybe target that field with that drug. Does that make sense? Okay. So a single blind study is the idea that you guys the patients never know what they're taking or what they're getting, whether they're getting the placebo or, you guys know what the placebo is? Okay, so the knowledge of me taking a substance is going to create a psychological reaction, and it releases chemicals in my body that might be the reason for my health improvement. Does that make sense? Just knowing that I've gotten something. Let's say if it's like a diet pill, like people take like hydroxycut and stuff like that, right? If you do any of the research on that stuff, there are no studies that say it's effective, okay? but people psychologically take that and it releases chemicals, and that can be the reason for the weight loss. Does that make sense? Okay, so we try to mitigate that. So a single blind test says, I, as the researcher, know who is getting who's getting the placebo and who's getting the actual drug. Okay, now that can create confounding variables. If I'm a researcher and let's say I'm like the head researcher and I'm working with the doctor and I go talk to each patient, my interactions with the patient, knowing what I know, whether they're getting the placebo or not, I might subconsciously give like body language or statements that can lead to them interpreting that they know they're getting the placebo. Does that make sense? Okay. So what we prefer to mitigate that is that we do double blind tests. So a double blind test says I might be the head researcher, but I don't know who's getting what. And when I don't know who's getting what, I can't have those conversations that might just subconsciously might lead a person to believe that they're getting the drug or not. Does that make sense? Okay. So it eliminates all potential like psychological impacts of our social interaction. Okay. That is what we look for. If you're looking at the vaccines right now that they're coming out with for the coronavirus, they're all double-blind studies. That's the benchmark. That's the standard that everybody looks for in studies to determine how effective something is. Yes. Okay. So yeah, good question. So I might be the head researcher. I don't know, but the person collecting data, like it might be an undergrad student or something like that, because a lot of people that are doing this are like attached to universities. So they have like techs and undergrads and that kind of stuff that are collecting the data, and they know, but those people never have contact with the actual patient. Who? Like the undergrad or whatever? The person that's working at the tech? They go through certain require like interactions where that like each of you is like given a number. Okay, that person is the only person that deals with those numbers and understands who's getting what from those numbers. And I just, as the head researcher, I never see that stuff. I just get the results. Does that kind of make sense? So they go through protocol to make sure to guarantee that nobody gives the head researcher any insight on who has the legit drug and who's getting the placebo. And there are like there's an entire board of like statistics and like operational things that like govern how you do these things. Like there's oversight committees and all that kind of stuff that make sure that your study is up to par with those codes and stuff, those procedures. But that's where we see inferential statistics in it, and it's based off taking a sample out of a population and collecting that data from them, and then being able to make a statement of confidence on whether the drug or whatever the treatment is was effective or not. Okay. When we talk about when I say when we talk about treatment doesn't have to be like pharmaceutical. It doesn't have to be a drug. Like a treatment could be, maybe I want to see if, I talked about having laptops and whether that increases your score on like state tests or anything, or maybe the ACT. Well, the treatment would be having the laptop. Does that make sense? And the control group would have been the group that did not have the laptops. Okay, so those are things that we can talk about later on when we get more into like the inferential statistics process. So that's the bulk of the class. That's later on, it's like chapter 4 or 5, we start to get into that, and that then is pervasive through the rest of the course. Okay, early on we'll talk about descriptive statistics, some probability stuff, but that all then morphs into inferential statistics. Key terms, we go down to probability. Okay, so probability is just the likelihood of something happening, right? Okay, so probability is a mathematical tool used to study randomness. Okay, you think about winning the lottery, it's random that you win the lottery. Okay, so it deals with the chance or the likelihood is the word that you're going to see most often of an event occurring. When we talk about probability. We like things to be fair, meaning that your outcomes are equally likely to occur. So if I have a coin, okay, tails is equally likely to occur as heads, right? That's a fair coin. If I roll a dice, a 1 is likely to occur as 6s. That means that's a fair dice. Each face has a 1/6 probability of occurring, okay? When we deal with probability, we've talked about this when you guys were in geometry, but we'll do it again when we get there in this course. There are two types of probability that we think about: expected, theoretical probability. Okay, and that is what you assume to be true off of essentially theorem, what should happen based off of mathematical principles. Okay, so if I flip a coin 100 times, what should happen? Expected to happen. 50 tails, 50 heads, right? It's a fair coin, okay? Now, if I were to do that, what really happens? Maybe 40, 60, 55, 45, 30, 70 maybe in some cases. Does that make sense? 57, 43, okay? So and we'll do the simulation like that later on, but if I just flip a coin 100 times, I would be a betting man. As being a betting man, I would guarantee that if every one of you had a coin flipped it 100 times, not one of you is going to get 50-50. Okay? But now if you all did it, flipped your coin 100 million times, okay, I would be more likely to bet 50-50. And we'll talk about that simulation later on. But that's the law of large numbers, okay, which the law of large numbers you see up there, and we've talked about this. Let's say Lex plays baseball, right? Lex, you ever been in you awake? Okay. You ever been in a slump? Like, what's a slump for you? Like 0 for 20? You ever been 0 for 20? Yeah, me neither. But you've probably been 0 for 30. Okay. So let's say it's 0 for 30. We're playing baseball, playing softball, those types of things. Somebody hasn't had a hit in a long time. What does everybody on the team say? He's in his next at bat, he's what? Well, yeah, but he's due, right? He's due. He's bound to get a hit because he's been hitless for so long. Law of large numbers says he can't go hitless forever. Okay, his average, maybe he's a 300 hitter. Okay, and he's gone 30 at bats without a hit. The law of large numbers says he is going to get a hit sooner than later. Okay, so I mean, if you think about like all the multi-million-dollar contracts that are signed out to basketball players, that are signed out to football players and baseball players, a lot of those contracts are heavily based on probability of what those players have done and what they're going to do then based off those probabilities in the future. Okay. So law of large numbers says the more times that you do something, the more times you do an experiment, the more likely that your outcomes are going to model what is expected or what is the theoretical probability. Okay. So we have theoretical probability or expected probability, and that's what we should expect to happen based off mathematical concept. Experimental probability is actually doing the experiment. It's actually flipping the coin. Okay, it's actually taking this group of people and treating them with a particular drug. Okay, that's the experiment. Does that make sense? Okay, the more that we do that experiment, the more our results turn to what we should expect. Okay, and the law of large numbers allows that. So those three concepts kind of linked together are kind of the underpinning concepts for this course. All right, so in order to address a lot of the questions in this class and deal with being able to answer statistical type questions and relationships, we need to be able to identify two things. We need to identify a population and a sample, okay? And then from those two things, it breaks off to what we call a statistic and a parameter, okay? So first thing we're going to do is talk about a population, okay? A population, okay, is generally the group that we're trying to study. So earlier in my cancer patient scenario, my population would have been all people that have lung cancer, okay? Let's say if I'm Pfizer and I'm making drugs, I'm a large pharmaceutical, I'm interested in being able to sell my pharmaceutical drugs to everybody in the world, right? Okay. So let's say that I'm trying to target everybody that has lung cancer. That's a lot of people, right? I can't go and ask and communicate and talk to all those people because it's costly. So I can't really investigate that entire population. If I do investigate the entire population, it's called a census. Okay? So I can't. We're in the middle of a census right now. Okay? Where the government is trying to reach out to every single person in the United States. Okay? Of legal age, obviously. Okay? But if I want to study a population, it is almost impossible in every situation to do so. Okay? So what we do is we take a smaller section of that population. The smaller section of that population is called the sample. Does that make sense? Okay? So if you look up there, it says you can think of a population as a collection of persons, things, or objects under study. Okay? I've jumped down. I'm going to skip that exercise. We'll come back to it in a minute. And we look at the sample. It says sample is used to study the population. Okay? We select a sample, and there's going to be techniques for us on how we collect a sample because we want to eliminate bias in our sample. Okay? We want to eliminate certain maybe characteristics that the sample has that maybe the population in general does not have. So the idea of sampling is to select a portion or a subset of the larger population and study that portion. Okay. Once we get the information from that sample, that portion, then we can make assumptions about the population from that. Okay. Now we look at this exercise. Okay. I'm just going to look at this example right here, and it asks us to find the population. Okay. So when I read these, or when you read these, there's usually going to be two groups. There's going to be a group that is larger and a group that is smaller. The larger group, the population. Smaller group, the sample. Does that make sense? That's always the situation. So when we read this, you see two groups of people being expressed up there. It says we want to know the average amount of money first-year college students spend at San Jacinto College on school supplies that do not include books. Okay. So is that a group of people? First-year college students at this college, right? Okay. So there is one group of people. Let me highlight that. So first-year college students at that college. Okay. It says we randomly survey 100 first-year students at the college. Is that another group of people? Now, which one of those groups, the yellow one, does the yellow one belong to the green, or does the green belong to the yellow? Do the 100s randomly surveyed first-year students, do they belong to the yellow? Are they a subgroup of the yellow? Yes. Okay. So the yellow highlighted group of people must be the population. Does that make sense? Okay. That's the group that we want to study. Now let's think about some colleges. If I go to Ohio State, there might be 30,000 first-year students there. Okay. Resource-wise, I can't go talk to every one of them. Okay, I can't give a survey out. I can't give a mailer out. Imagine mailing, just printing off and mailing to 30,000 people, just the cost of a stamp. How much is that going to cost you? How much does a stamp cost? About 50 cents, right? One stamp. Okay. Yeah. So then, yeah. So if I send to 30,000 people, that's a $15,000 bill just on stamps, right? Okay. So resource-wise, that doesn't make a whole lot of sense. So we try to communicate to 100. Okay. Now, I know this example says do not include books, but let's ignore that. Let's say we are including books. Okay. And let's say that I go and I just hang out in front of the college bookstore and I survey the first 100 people that walk into that college bookstore. Are those 100 people's surveys, the information they give me, is that going to be resembling or corresponding to the entire population? If you guys were going to go get a textbook, are you going to go straight to the bookstore and pay manufacturer's suggested retail price, MSRP? No, why not? Yeah, so some people are going to get those books for pennies. They're going to get on Chegg.com. They're going to get on Amazon. They're going to rent their textbooks, that kind of thing, right? Okay. If I'm going to the bookstore and I'm buying all my books brand new, I've got money to spend. Does that make sense? Okay. So sampling those 100 people, there's kind of like an income disparity between those 100 and the other however many thousand first-year students there are. That would not give me a good representation of the population. Okay, so there's bias in that sampling. So what we would want to do, there are techniques, and there's sections dedicated solely to this, but we'll talk about how we go through and make sure that the people we choose to survey are randomly chosen, so that I get some of those people that show up to the bookstore, but I also get some of those people that rent their textbooks for almost free. Does that make sense? Okay, but that's how we identify the population, how we identify the sample. Okay. We'll scroll down here to where it says parameter. Okay. A parameter is a number or a quantity that represents a property of the population. Okay. So it's something that describes the population. So it's because it takes a lot of time and money to examine the entire population. We already talked about that. Usually parameters are unknown. Okay. Usually a parameter is unknown. But this is the way I remember these. Parameter starts with P, population starts with P. So they link together. They're stuck together. Okay? But a parameter, a lot of times, we don't know. The parameter is ultimately what we're looking for in this scenario. If we think about this, it says we want to know the average or the mean for first-year college students. Okay? That is a quantity, okay, or a number attached to the population. Would you guys agree with that? Okay, so that's the parameter. Now, we talked about how that's not feasible to know, okay, because it's impossible to collect all the data from every single one of those people. So what do? Is that we look at the sample. If I take 100 people, is it easier to find the mean of 100 people? Does that make sense? Okay. So it's not written in this exercise, but the sample here, being those 100 people, the statistic, okay, the statistic is the average amount of first year let's write this. Average amount of, I'm just going to put money spent by 100 surveyed students. Something like that. That's the statistic. A statistic, it's got to be the exact same quantity that is being measured about the population, okay? So if I wanted to measure the mean amount of money spent by first-year students, I'm not going to collect average height of these 100 people. Does that make sense? Average height and average money spent, they're not the same thing, okay? So what I'm studying in the population has to be the exact same thing I'm studying in the sample. Is that all right? Okay. A statistic pairs with sample, okay? So parameter comes from population, statistic comes from sample, okay? P and P, S and S, right? Does that make sense? Okay. I think it makes sense to look at this picture a little bit here. This gives a little bit better of an idea of what's going on. Now, I know I didn't do a good job of cut and pasting this, so it might be a little blurry on your paper, okay? But the idea is that we've got this population, we've got this group of people here on the left, okay? And I want to know something about them. I want to know their parameter, okay? Now, this letter down here, this is the Greek letter. Anybody know what letter this is in Greek? Anybody in physics ever see that? That's the Greek letter mu. Yeah. What? Yeah. Okay. So mu is that letter, and that's what we refer to as the population mean. Okay. Or the population average, but we use the word mean instead. Like I said, that's something that we can't figure out. We don't have the resources, the time, the money, the ability to gather that and learn that, figure out that that parameter. Okay. So what we do is somehow choose. Maybe we choose that person, that person, that person, maybe that one, and we bring them over here, and we put them in our sample. Okay? And we'll talk about how we randomly select those people. Okay? Now, we can target 6 people. Okay? Now, usually, in the studies that we do, it will tell you how many people you need so that your data can be verified, that your data can be accepted. But we take so many people and now we investigate their mean. Okay, we call it the sample mean, and that's what this, we read this little thing down here. That's called X bar. Okay, it's got a bar over the top of it, right? So that's the sample mean, and I'll show you how we collect that data and how we determine and calculate X bar and mu and all that kind of stuff later. But what we've basically figured out is if we randomly chose these people in an appropriate way, we have enough people in our sample, okay, we can make the argument to a certain degree of confidence that the statistic we were able to determine corresponds or models the parameter. Does that make sense? So we might be able to, out of these 100 people that we chose, we might be able to figure out that their average money spent on school supplies, let's say, is $330. Well, if that was true for my sample and my sample was chosen correctly, then we can say that $330 is also a pretty good estimation for the parameter or what the entire population is spending. Does that make sense? Okay. So it's very difficult to do something for the large group. So we break it down into smaller groups, learn what we can say about the smaller group, and then make the inference that that smaller group's information corresponds or parallels to that of the population. Okay? Does that make sense? Okay. You guys have any questions on this stuff yet? We didn't get very far in the first period today because of the lockdown drill. Okay, so I'm going to stop there. Tomorrow we'll finish up these last couple notes, talking about basically using the same example, but talk about what the variables are and what the actual data is. But that'll be tomorrow. I've posted 2 things, and I'll show you where they're at. So I can get this on video, and the online students can see this. Under the statistics course, there is a quick assessment here. Okay. If I want you to do anything in Schoology, the assessments are going to come underneath the sections. That's the only way I can do it. But if you click on that statistic versus population, all they're going to do when you take this, looks like some people have already taken it. If I look at this question here, what is it going on? Oh, I can't view it as a student. Well, basically all it does is it reads you a question. It says, like the height of every basketball player on the 1996 Chicago Bulls. Is that a population or is that a statistic? Well, I'm choosing every person off of that team. Does that make sense? So that's going to be the population. If I were to take the 5 starters of the 1996 Chicago Bulls and measure their height, that would be a sample out of the team. Does that make sense? Okay. So you're going to read those scenarios. We'll talk about those. It shouldn't be something that's really mind-blowing. Gives you, I think I got 10 questions in there. Do that. It's supposed to be out of 100? Yeah. 100 points, I think, but I don't care. It's out of 10. Then in my open math, section 1.1 is open. There's 5 questions there. That shouldn't take very long to do either. Questions? Is good? Yes.